In this video, we'll explore the first part of Chapter 13, which focuses on the structure and function of carbohydrates. This is the foundation for understanding glycobiology, glycan chemistry, and the many roles that carbohydrates play in living systems. Chapter 3 has three major sections. First, we're going to look at carbohydrate structure basics, and that's this video. Next, we'll examine important biological functions of carbohydrates, and finally, we'll touch briefly on biochemical methods in glycobiology. By the end of this portion of the chapter, 13.1, you should be able to classify monosaccharides, interpret Fisher and Haworth projections, identify stereochemical relationships, understand cyclization and mutarotation, and determine whether a sugar is reducing. Later on, we'll talk about common monosaccharide derivatives and glycosidic linkages. So carbohydrates are among the most abundant molecules on Earth. They contain only carbon, hydrogen, and oxygen, and follow the empirical formula CH2O sub N, where N is 3 or more. So the H2O part is where the carbohydrate name comes from. Carbon, and then hydrate, the water. So you'll also hear carbohydrates referred to as glycans. That's just a synonym that we use. It's a broad term for simple sugars, polysaccharides, and glycoconjugates. So simple sugars are going to be the monomers that are used to make polymers, to make carbohydrate polymers. Hydrate polymers. And then polysaccharides and glycoconjugates are larger biomolecules, macromolecules that incorporate these simple sugars into their structures. So one of the most important themes when thinking about carbohydrates is structural diversity. And that stems from the diversity of monomers that we can have. So monomer diversity yields a great deal of structural diversity. So when we talked about our previous biopolymers, DNA and RNA, so our nucleic acids, they only had 4 building blocks, right? So if we look at our previous polymers, our nucleic acids have 4 monomers. Proteins, we have more diversity because we have 20 monomers. With carbohydrates, we have many more different types of monomers, almost an infinite diversity in terms of the basic building blocks themselves. They can be chemically modified, and they can link up in different ways. So polymers have the most structural diversity of any of our classes, and that makes them very good for the purposes of specific molecular recognition, as we'll see when we talk about function. Okay, so carbohydrates are not just energy sources. They've got lots of different purposes in biological systems. So obviously they're used to store and generate energy. That's one of their main uses, and certainly that's the most common use in terms of on a per gram basis. But again, because of this structural diversity, they're very good for molecular recognition. They can be used in structural ways. So they can be used for cellular protection. They can be used for cell adhesion. They're also very good for making biological lubricants and also, again, building and maintaining strong structures. So, for example, cellulose and chitin. Chitin is the main component of exoskeletons, right? And cellulose is what gives plants structure. So we're going to start out by introducing some basic carbohydrate terminology. We're going to develop in further sections as we learn full naming conventions, but these are more general terms. Okay, so these are general terms. So first of all, the term monosaccharide refers to simple sugars and their derivatives. These are going to have 3 to 9 carbon atoms, and again, can be used to build polymers. Okay, to build polymers. Oligosaccharides will have more linked monosaccharides together, and they would go between 2 to 20 monosaccharide units. So these would be the carbohydrate equivalent of peptides, right? We have amino acids, then peptides are sort of short groups of amino acids linked together, and then we have proteins which have many amino acids linked together. So oligosaccharides are short strings of monosaccharides. And then our polysaccharides are long chains, sometimes thousands and thousands of units long. And then glycan is just a generic term that encompasses both oligosaccharides and polysaccharides. It's more of a catch-all. All right, so what's a carbohydrate? Again, carbohydrates, any molecule composed of monosaccharide units or a compound that yields monosaccharide units when we hydrolyze it. Okay, they have to follow this general formula, again, the CH2O, where the number of carbons is going to vary between 3 to 8. So our smallest monosaccharide will have 3 carbons, our largest will have about 8. Monosaccharides, okay, are classified by the number of carbon atoms, and we use Greek prefixes to say how many carbons there are. So we have things like trioses. So os is our suffix. Triose has 3 carbons, and let's say hexose has 6 carbons, pentoses have 5, tetroses have 4. Okay. They're also going to be classified as whether they have an aldehyde group or whether they have a ketone group. Okay, so aldehydes are aldoses. Ones that have a ketone group are called ketoses, and all of them will have one or the other. So the example shown on this slide, okay, is ribose. So ribose is a pentose. It's a 5-carbon sugar. And every single structure that you see on this slide is a different representation of ribose, or a different structural form. So you'll notice that we are not showing all the we have some representations that don't show all the carbons as C's. Actually, none of these show all the carbons as C's. We often hide the hydrogens, so if you don't see anything attached to where you know the carbons are, you can assume that those are hydrogens. Okay, so again, all of these are forms of the sugar ribose, and you should be familiar with that from our study of RNA nucleotide structure. Okay, so trioses are the smallest monosaccharides. They have 3 carbons, right? So we've got 3 carbons. And when we write carbohydrate structures for simple sugars, and we're writing them in the straight chain or linear form, what we're going to do is we're going to number our carbons from the most oxidized end. So remember that our definition of oxidized in biochemistry, we have patterns that repeat. So oxidized is going to be look for the most bonds to oxygen, and you'll find that's your most oxidized end. Okay, so in this case, we have D-glyceraldehyde, which is an aldose because it has an aldehyde group, right? And so the aldehyde carbon is our most oxidized carbon, so that gets carbon number 1, and then we number moving farther away from that. And then we have dihydroxyacetone, which is a ketose, because, again, it has a ketone group. So instead of having a hydrogen attached to the carbonyl, it has an R group on either side, right? So an aldose is a monosaccharide containing an aldehyde, and the carbons are numbered beginning at the aldehyde carbon. A ketose is a monosaccharide containing a ketone group, and the carbons are numbered so that the ketone carbon has the lowest possible number, so it's going to be number 2. Okay, so the ketone carbon is number 2. And here, the aldehyde carbon is number 1. Okay. So one of the things that you will notice that is different between our aldose and our 3-carbon ketose is that the aldose has a chiral center, right? So glyceraldehyde has a chiral center. Carbon 2 has 4 different things attached to it. And dihydroxyacetone does not have a chiral center, right? In this case, our carbon has 2 hydrogens attached to it, and in the case of carbon 2, it's got 2 bonds to the oxygen, so that is not a chiral center. So this has a stereocenter. And now we're going to get into why carbohydrates have so much, one of the reasons why carbohydrates have so much diversity is because they can have a diversity of stereochemistry. So we're going to talk about stereochemistry now. So to remind you of some of the terms, or to give you a preview of some of the terms that we're going to use enantiomers as a term. We're going to use diastereomer. We're going to use the term anomer, and we're going to use the term epimer. So those are going to be our 4 terms used to designate. So these are our 4 terms used to designate stereochemistry or to describe it. Okay. So diastereomers and enantiomers. So enantiomers are mirror image isomers. So if we take our glyceraldehyde here, okay, and we reverse the stereochemistry here at that 2-carbon, okay, we are going to have the complete mirror image of this molecule, and we call those enantiomers, okay? So mirror images, okay? And that's going to be all the stereo centers in our molecule have their stereo center, the chirality around it, reversed. So enantiomers are non-superimposable mirror images. Glyceraldehyde is a classic example. And this is also our reference molecule for calling a monosaccharide D or L. Okay, so glyceraldehyde is our reference for what we call the D or L designation. So In organic chemistry, when you studied stereochemistry, you talked about optical rotation and you used terms like R and S. And that corresponded to how that molecule, that chiral molecule, would rotate optically polarized light. And it would do it differently if your functional group here was projecting off into one direction or the other. With carbohydrates, we do designate the stereochemistry at the highest numbered chiral carbon. In this case, there's only one, so that's carbon number 2. We designate it as D or L, and we do it with respect to glyceraldehyde. Okay, so D-glyceraldehyde corresponds to R-glyceraldehyde, and L corresponds to S-glyceraldehyde. But when we talk about other sugar monomers, D or L is not going to correspond to optical rotation. So that's just to let you be aware of that. Okay. All right. So, whoops. This slide kept pre-labeled, but. So now we're going to talk about Fischer projections. So they provide a simplified way to represent stereochemistry. They are not Lewis structures. Okay, so that's one key thing: is a Fischer projection is not a Lewis structure. Note there's no lone pairs shown. Okay, in a Fischer projection, okay, we start by putting the most oxidized group at the top. Okay, so most oxidized group at the top. And so our lowest number starts at the top, and we number carbons as we go down. In a Fischer projection, okay, horizontal bonds. Oops, and these are backwards. Okay, so in a Fischer projection, horizontal lines project away from you, and vertical lines project toward you. Okay. All right. So the D or L designation in glyceraldehyde, if you recall, was at the chiral center. Okay, and if in a Fischer projection we have the hydroxyl on the right side, hydroxyl on the right, that is equal to the D isomer. So when we have more than 3 carbons, we're going to have more than one chiral center. So in the case of D-glucose, we have 4 chiral centers here. I have them numbered with their carbon number and stars next to the chiral centers. Now, it's only going to be the highest numbered chiral carbon that defines it as D or L. So this is D-glucose because the hydroxyl group is on the right. Okay. So the D or L designation is based on configuration, not the optical rotation, and it's based on comparison to glyceraldehyde. Okay. So let's quickly draw L-glucose so that we can see what the difference is. Remember, so L-glucose is going to be a full mirror image. So that's going to be an enantiomer, full mirror image. And so we would reverse the chirality at every single chiral center. So if I want to draw L-glucose, I have to fit 6 carbons in. Hold on. So let's go 1, 2, 3, 4, 5. All right, so here's my CH2OH at the end. Here is my aldehyde group at the top. And now in D-glucose, the hydroxyl's on the right. So it's going to be on the left in L-glucose. At carbon 3, it's on the left in D, so it'll be on the right in L. And I'm going to reverse it on carbon 4 and on carbon 5. All right, so I'm not going to draw the hydrogens in here. You can just add those in your mind. So notice that it's I I can still tell that this is going to be L-glucose, or that this is an L isomer just by the position of the highest numbered chiral carbon, because the hydroxyl is on the left, right? So this is L-glucose, the full mirror image of D-glucose. So the thing that we're going to learn is that the name, the common name glucose, refers to the chirality at these other three carbons, and then the D is the chirality at this carbon. So if I have diastereomers that have different chirality at these carbons, they're going to have a different name. All right, so enantiomers versus diastereomers. Remember that our enantiomers are mirror images. They're going to be the same except for the stereochemistry at one chiral center, and they're distinguished by having D or L preceding the common name. Okay, so D erythros and L erythros are enantiomers. Everything's the same except that one stereochem center. Diastereomers, okay, are not mirror images. Okay, they're given different common names. And so you can have two diastereomers that have the same D or L designation, or they can have different ones. Okay, so for example, D erythros and D threose are diastereomers. Or you could have D galactose and D glucose. Okay, so let's look at an example of diastereomers. So we can have, if we just look, okay, we can have the same D designation, right? Because our highest numbered chiral carbon here is carbon number 3, because this is a 4-carbon, this is an aldotetros. And here the stereochemistry at carbon 3 is the same, right? So that gives us our D. But when we look at the stereochemistry at our other chiral center, which is carbon 2, okay, we have different stereochemistry there. So that's where we get the different names. So this is what makes it threose, and this is what makes it erythros. All right. So, and here we see that diastereomers are going to have different names. Now, so diastereomers have different names. Okay. But remember that these two, okay, are enantiomers of one another. These guys are also enantiomers. All right, so there's one other term, okay, that we're going to talk about, because if you look at these, okay, threose and erythros differ. So D-threose and erythros differ at only one chiral center. All right, and so those get a special name. Those are called epimers. So diastereomers that differ at only one position are called epimers. And it'll be a little bit clearer when we get to longer chain monosaccharides like hexoses, and because then we'll be able to see things that differ at 2 centers versus the 1. All right, so let's look at ketosis for a second. This is what these are what enantiomers of a ketotetros looks like. So the ketotetros erythulose, okay, has only 2 enantiomers and no diastereomers because it has fewer stereocenters, right? So let's look. We have So we've got a stereocenter here at carbon 3, okay? And so we don't have different common names, right? We just have our D and our L. If we had another stereocenter, then we would have the designation of D or L, and then we would have two different common names, okay? All right, so aldotetroses, so we're back to aldehydes, right? So remember, here's our ketose as our most oxidized carbon as number 2. Most oxidized carbon is number 2, so that means it's a ketose instead of an aldose. Okay, so aldotetroses are going to have 2 chiral centers, and that gives rise to 4 different stereoisomers, right? 2 D forms, D-threose, D-erythrose, and 2 L forms, L-erythrose and L-threose. So that means we have a total of 4 different possible stereoisomers, right? 4 different stereoisomers. So hopefully this gives you a clue that as we increase the number of carbons, we're going to have more and more different stereoisomers. All right, so again, you're going to need more carbons in a ketose to have more stereoisomers than you would for an aldose, again, because of the position of the most oxidized carbon. So ketoses typically have fewer stereocenters than aldoses with the same carbon count. Okay, so ketoses have fewer stereocenters than aldoses with the same number of carbons. So for ketohexose, so if we go down here, when we have 6 carbons, right? We have 4 different D stereoisomers, okay? So I'm going to zoom in on those for a second. So you'll notice, right, all of these are D isomers. So there's going to be another 4 that are L isomers. So we'll have L-psychose, my favorite monosaccharide because of the name. And then we have L-fructose, L-sorbose, and L-tagatose. So again, notice that the name of the sugar is going to change based on the stereochemistry at our other 2 stereocenters, right? So if we look at the stereochemistry here, right? So we can have our hydroxyl groups both on the right. We can have one on the left, one on the right, or we can have one on the right, one on the left, or we can have both on the left, okay? So that's the stereochemistry that gives the common name, okay? The stereochemistry here gives common name. And by common name, I mean the psychose, the fructose, sorbose, or tagatose part. And then the stereochemistry here gives D or L. All right, so this is for ketoses. And so again, we have 4D and 4L, so that makes 8 ketohexoses. So let's look at how this compares to aldoses, which I had told you have more more stereoisomers for the same number of carbons. So if we look here, by the time we get to the aldohexoses, we have 1, 2, 3, 4, 5, 6, 7, 8. So we've got 8 times 2, 16, because these are just the Ds, right? And then the L's give us another 8. So we have 16 aldohexoses. Okay? And these have names like allose, altose, glucose, mannose, gulose, idose, galactose, and talose. So this is a good time to get back to our terminology of the epimer. Okay, so glucose and galactose, let's consider these. So glucose and galactose. So if we look at the stereochemistry, all right, so we've got carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6. So for D-glucose and D-galactose, okay, the stereochemistry at carbon 5 is the same because that's my D or L, right? And if we look at carbon 2, which is a stereocenter, it's the same at 2. So we'll do glucose and galactose, and both D isomers. So we've got the same at carbon 2. We have the same at carbon 3, right here, both on the left on 3. At carbon 4, it's on the right in glucose and on the left in galactose. And then carbon 5 is the same. So these differ only, differ only at carbon 4, okay? And so that's only one position difference. And so we call those stereoisomers epimers. So that's the special name we give to those. And we would say that galactose is a C4 epimer of glucose. So it's all the same as glucose except that one position. All right. So now you may be recalling from organic chemistry, right, that some of these functional groups have a possibility of chemically reacting. Okay. So we have aldehydes and ketones, and it turns out that aldehydes and ketones can react with alcohols, right? And what's our functional group for the alcohol? It's a hydroxyl. And our sugars have lots of hydroxyl groups. So monosaccharides can cyclize when our alcohol group will attack the aldehydes or the ketones. So when this happens, and so if we have our hydroxyl on the 5 carbon reacting with the hidden by my figure here aldehyde group, then what you get is you get a ring that closes. Okay, so here is showing the reaction right here. So this is carbon 5. There's the hydroxyl on carbon 5. Okay, so it's the one I circled on the left, and it's reacting with the aldehyde group, and it's going to form a closed ring where the oxygen becomes part of the ring. So the oxygen atom is part of the ring. Okay, and this is carbon 6 right here. This one right here is carbon 5. And one of the things that you should note is that the site where the ring has closed, this was our carbon number 1, right? That was our aldehyde carbon, becomes a new stereocenter. It now has 4 different things attached to it. So we have to have a way of designating that. And so we now call this the anomeric carbon. And we have two possible configurations stereochemically at that position. We have with the hydroxyl down below the ring or with it above the ring. And we call those the alpha and the beta anomers. Okay, so we're going to talk about Haworth projections in a minute, but let's look at the cyclization of glucose first. Okay, so glucose provides us with a really good example of the cyclization of a linear sugar. The reaction of the hydroxyl on C5 right here with the aldehyde group produces a six-membered, what we call pyranose ring, right? And we'll see why it's called pyranose in a few slides. So our new stereoisomers, so you'll notice that these reactions are all double arrows. That implies they're reversible and that they are in equilibrium with one another. So we have our straight chain form, and then we have our two cyclic forms here. Okay, so our new stereoisomers are called the alpha and beta anomers. So our alpha anomer, okay, has the hydroxyl group trans, which means on the opposite side of the ring, to the CH2OH group. Okay, so, whoops. So anomeric hydroxyl is opposite trans side of ring to the C6. Okay, and then in the beta anomer, we have the hydroxyl and the C6 on the same side of the ring. So this is alpha, and beta is the anomeric hydroxyl on same side as C6, okay? All right, and so we would say that was cis to that group. So our anomers are going to begin, because these processes can be reversed, right? So we can have our cyclic form can open up into the ring form, okay? We can get rotation around this bond here. It's a single bond, so when this is open, this thing can rotate. And then when ring closing happens again, we can get interconversion between the alpha and the beta anomers. So anomers interconvert via a process that we call mutarotation. It requires ring opening. It's a normal process, and it occurs because an aqueous solution, our stable cyclic hemiacetal here, or our hemiketal if we started with the ketone, can open into our straight chain aldehyde or ketone. And then that open form can cyclize again, and if we had rotation around this bond, we can wind up with the opposite anomer if rotation occurred in the meantime. So the rate at which this process occurs, mutarotation, it can be influenced by temperature, pH, solvent polarity, and we'll talk more about that in a minute. Okay, so Haworth projections, okay, are simplified drawings that we use to represent 5- and 6-membered sugar rings. In these depictions, our cyclic hemiacetal is shown as a flat pentagon or a hexagon viewed on the edge. By convention, our anomeric carbon is placed on the right, okay, and you'll notice that right here it has a squiggly line. When we have the squiggly line, that means that this could either be alpha or beta. So alpha or beta. And if this is not attached to anything and mutarotation can occur, then it's going to open up and it will be one or the other at any moment in time. Okay. And then the ring oxygen's usually put in the kind of back right. All right. So so our rules of thumb are for interpreting our Haworth projections. If it is down in a Haworth projection, so let's just look at this right here. So this is carbon 2, okay, and the hydroxyl is down. So if it's down in the Haworth, it's going to be right in the Fisher projection, okay? So let's look at carbon 2. Here's carbon 2. That is to the right in the Fisher projection, and in the Haworth, it's down below the ring. Okay, so that's how you will be able to convert between a Fisher and a Haworth projection. And then if it's up in the Haworth projection, it's going to be on the left in the Fisher. So here's some more examples of Haworth projections and how they're typically depicted. In that previous slide, it was hand drawn, so you didn't see the full kind of wedge that you see here. So when a sugar has 5 or 6 carbons, okay, it can cyclize in one of 2 ways. So it can form a 5-membered ring. So I'm counting the oxygen as a member of the ring. So it can form a pentagonal ring, or it can form a hexagonal ring with 6 members of the ring. The pentagonal form resembles the organic compound furan. So that leads us to call the resulting cyclized sugars furanoses, okay? And then for the hexagonal forms, they look like the organic compound pyran, and so we call those pyranose structures. Okay, so remember that our hemiacetal or hemiketal that's formed is always capable of reopening and recyclizing, and you not only will get mutarotation and changes between your alpha and beta isomers, but you can go from a pyranose form to a furanose form. So a fun example of this has to do with the sweetness of honey. So honey's perceived sweetness it decreases when you heat it, because the primary sugar fructose originally it will start in the very, very sweet at low temperatures beta D pyranose form. So honey has 2 forms, our beta D pyranose form, and that's the form that tastes very sweet. But when you heat it up, it affects the equilibrium of that ring opening, and so what happens is beta D furanose form tastes less sweet, and it's favored at higher temperatures. So if you put honey in your tea as it cools, it will start to taste sweeter, because as it cools, the equilibrium shifts back to the pyranose form, and it spends more time in that sweeter tasting form. So that's just kind of a fun thing. All right, so one thing I'm just going to mention as an aside before we go on is in organic chemistry, you talked about chair and boat conformations. These have very different thermodynamic stabilities, and so most of the time with our pyranose sugars, they will be in the chair conformation. So we're not going to talk too much about chair and boat. Okay. All right. So Fisher versus Haworth representations. I just want to show you this slide. We can write a Fisher representation for a cyclic sugar. We usually, again, will put the oxygen on the right, and we will, draw links between the carbons that are connected. So this just shows you how stereocenters translate into ring structures. So we can write the Fisher projection of a cyclized sugar. We're mainly going to use Haworth projections when we're dealing with cyclic sugars. But let's talk for a second about naming, or get back to talking about naming. So recall, we have to give all the parts that we can designate about the stereochemistry when we name a sugar. Okay, so the name of this is alpha D glucose, but to be most specific, okay, if it is in a particular ring form, if it's either shown in that form or if it's locked into that form because of, a glycosidic bond between, the anomeric carbon and something else, we should designate whether it's the pyranose or furanose form. Okay, so we would start with the anomeric form if it's cyclic. Well, alpha or beta. Then we would designate it as D or L. Okay, then we would do the common name and then say whether it was pyran or furan based ring, so either a 6-membered ring or a 5-membered ring, and we always end with the suffix "-ose". Okay, so the proper name for this is alpha D glucopyranose, and if it were in a furan form, it would be in the furanose form. All right, so we're mainly going to use Haworth projections when dealing with cyclic sugars. And again, we like to abbreviate things and do things as quickly as possible. So the abbreviated Haworth does not have any of the hydrogens. So again, you can understand that there are going to be hydrogens here to fill out the octet of the carbons when they're not explicitly shown. Okay. All right, so a couple things. How do I find the anomeric carbon? And how do I know if I'm looking at a D or an L sugar if it's in its cyclic form? So let's talk first about how I find the anomeric carbon. And it's actually pretty easy to find your anomeric carbon. It's going to be the one that is bonded to 2 oxygen atoms. Okay, so here we have some pyranose forms of hexoses and our anomeric carbons. I'm going to change the color of my highlighter because it won't show up if I use the pink on the pink. So here is my anomeric carbon. And if we look down here, right, here's my anomeric carbon. And what am I looking for? I'm looking for, is it attached to 2 oxygens? So I have 1 oxygen connection here, and I have 1 oxygen connection there. All right, and this is going to work for both aldoses and ketoses. Okay, so right now I'm showing you an aldose. Okay, on the next slide we'll distinguish an aldose from a ketose. But let's pause for a minute to say, what would an L sugar look like in a Haworth projection? Okay, so remember, we're going to use glucose as our example here. So this is alpha D glucopyranose. So we're going to make alpha L glucopyranose. And so the rule is D or L, they're enantiomers, they're mirror images. So the stereochemistry at every chiral carbon is going to be different. So I'm going to start by drawing my pyranose ring. Okay, let's leave the alpha alone for a minute, right? So we're going to change the stereochemistry at every stereocenter. So at carbon 2, it's down in D-glucopyranose, so it's going to be up in L-glucopyranose. Carbon 3, it's up in D, so it'll be down in L. Same thing at carbon 4. So now I'm at carbon 5, okay? So I have to change the stereochemistry there, but I don't have a hydroxyl there because that oxygen reacted and it's in the ring. So what I have to do is I have to change where that CH2OH is projecting off of, okay? Now, let's go back and place our anomeric hydroxyl. So we said that alpha is going to have things trans to that carbon 6. So I'm going to have that up here. And that will also follow my rule, right? That in my mirror image molecule, every single stereocenter is switched. Okay, so that's what L-glucopyranose is going to look like. So if you're looking for D or L, so when looking at a Haworth projection, okay, if the CH2OH is below the ring, the sugar is an L sugar. Most of the time you'll see D sugars and you'll see it above the ring. Okay, so this is what you look at to see if it's D or L. So it's D there, here it's L. All right. So distinguishing an aldose from a ketose. How do we distinguish a cyclic aldose from a cyclic ketose? First, we're going to find our anomeric carbon, and we're going to look for the CH2. Okay, so in a cyclic form, okay, our anomeric carbon is always going to be attached to 2 oxygens. So here we go. In this one, it's attached to 2 oxygens. In this one, that carbon is attached to 2 oxygens. So my little blue stars are designating the anomeric carbon, right? Now I'm going to look at what's attached to the anomeric carbon, right? So in the case of an aldose, right, it's just going to have the hydroxyl because your hydroxyl that reacted with the aldehyde was reacting with carbon 1, and that turns into, again, it leaves you with a hydroxyl group, okay? Whereas with a ketose, okay, you're still going to have that hydroxyl, but you're also going to have a CH2OH group, right? Because that was attached to the carbon. So this turns into becomes the hydroxyl. Okay, that becomes that. So over here, that becomes the hydroxyl, right? And then this becomes this guy becomes the ring oxygen. Okay, this guy becomes the ring oxygen. All right, so that's how you tell, right? If you find the anomeric carbon, and if it just has an OH and a hydrogen, it's an aldose. And if it has an OH and a carbon with stuff attached, it's going to be a ketose. Okay, so the last thing that we're going to discuss in this video is reducing sugars. So one term you'll hear used to describe sugars is reducing. Okay, a sugar is considered a reducing sugar if its ring can open to reveal a free carbonyl group. Okay, so here I have my hemiacetal, right? And that hemiacetal can open to an aldehyde, right? And so we've got my COH, right? And so aldehydes they'll open to reveal a free carbonyl group, and that's going to be able to reduce metal ions. So this here can reduce metal ions. Okay, and the reason it can do that is because the aldehyde is readily oxidized to a carboxylic acid, and in the process, okay, it's going to donate electrons to reduce the metal ion. Okay, so again, this is only going to happen if your anomeric carbon is part of a hemiacetal. Okay, it's not going to happen if there's another bond to carbon here. So when we talk about linking sugars together via glycosidic bonds, we're going to be locking things into their ring closed state. But if a ring can open, okay, then it can undergo this redox reaction with a metal. And we call that a reducing sugar. And so one of the common tests, there are tests to see if you have reducing sugars or not. They're called Benedict's or Tollens tests. They have silver ions, for example. And there's a really fun thing where you can make a silver mirror by exposing a solution of silver ions to a reducing sugar, and the silver gets reduced to metallic silver, and it coats the glass of the reaction vessel, and it makes a very nice shiny mirror. So as long as your anomeric carbon is free to open, it can undergo this reaction, and we would call it a reducing sugar. Okay, so if we have, again, we'll talk about glycosidic linkages that will lock things into closed ring form. And so you would have a negative Tollens test. But if your anomeric carbon is free to open, then you can have a positive test. So the aldehyde or the ketone group on a sugar is not the only functional group that can participate in chemical reactions. You'll notice that we still have a lot of hydroxyl groups here. So the next class, we're going to look at how we can increase structural and chemical diversity further by having reactions that will incorporate different functional groups at other positions. But that's going to end our discussion of monosaccharides for now.